Real exam questions. Question 41, minimum reinforcement of beams. Determine the minimum reinforcement, quantity and diameter, due to bending for a maximum crack width of 0.2 millimeters. The cross-section is 300 by 600 millimeters. The minimum tensile reinforcement we have to calculate. Steel quality is 500 megapascal and concrete quality 45 megapascal. We are not taking into account the compression reinforcement because this is only, it gives you only a small difference. The concrete cover is 50 millimeter. For crack control, the maximum crack width is 0.2 millimeters. The effective depth of the beam is the total height minus concrete cover minus the sphere diameter and minus the point of gravity of the reinforcement. We do not know the reinforcement yet, so we assume, because this is minimum reinforcement, that it will be very low, the reinforcement percentage, so we start with 14. If this does not work, then we have to redo the calculations with another diameter. So the D1, the position of the tensile reinforcement, is 67 millimeters, but it's different from 0.1H, which is 60. The concrete quality is different from 30. So this means that we have to adapt table 7.2N, which is giving you the maximum steel stress in function of the bar diameter to obtain a crack control of 0.2 millimeters. So this table was generated with those two conditions, but we are not compiling with those conditions, so we have to adapt this table. We do that by multiplying the diameter with a certain factor. In this factor is Kc, because it's bending, that's 0.4. The critical section is because it is bending. It means that this is half of the section is the critical section. H/2 is 300 millimeters. The FCT effective we take equal to FCTM, which is 0.3 FCK to the power 2/3, which gives you 3.8 megapascal. So we can calculate then phi star, and it's equal to 0.85 times the diameter phi. So the diameter that we use in the reinforcement must be multiplied by this coefficient to have an equivalent diameter that we will use in the table 7.2N. Again, we assume diameter 14 millimeter. With this diameter 14, we have phi star is equal to 12 millimeter. This is table 7.2N from the code. We are calculating the minimum reinforcement for bending, which is given by this formula. The fictive diameter to be used in table 7.2N is 12 millimeters, but it's in fact 11.93. So I will do the calculation with 11.93, but in reality, you can just take 12 millimeters and then the maximum steel stress is 240. But just to show how it works, I used the calculated one, 11.93. So it's just an interpolation from the table from those two values with those two values, and it gives you 241 megapascal. We have seen FCHV effective was 3.8, Kc was 0.4. Then you have the scale factor, K, which is an interpolation between 1 and 0.65. So it's 0.79 for the depth of 600 millimeters. And the concrete section in tension for the simplified, for simple bending is half the section. It's 90,000 square millimeters. So the minimum reinforcement is then Kc 0.4 times K 0.79 times FCT effective is 3.8 times ACT is 90,000 and divided by 241, the steel stress. And so we are at 450 square millimeters. 450 square millimeters is around 3 diameters 14, gives you 462, so that's okay. Then for brittle failure, the effective depth we have seen is 533 for a diameter 14. FCT effective was 3.8. So the brittle failure formula, this one, we can fill it in, and we have 315 square millimeters. But the absolute minimum is 0.13% of the section, and we arrive at 208 square millimeters. So the maximum of the two gives you the minimum reinforcement for brittle failure, and it's 315 square millimeters, or 3 diameters 12. So in principle, we should now, because this is diameter 12, change D, because D was calculated on basis of diameter 14. But this is only 1 millimeter difference, so we skip this. So the maximum or the minimum reinforcement is the maximum of crack control and brittle failure. So it's 462 and 339. It's 462. So it's the crack control that gives you the maximum amount of minimum reinforcement. And it is 3 diameters 14. Now, we have chosen now for diameter 14, and it gives you 462. But you can also choose a diameter 20, for instance, which is classic for a beam. If you don't know the diameter, you start with 20. You redo the calculation, and we find that we need 2 diameters 20 with a steel stress of 192 megapascal. This difference is it's bigger than the 462. It's a big difference. So we can use a smaller diameter. Suppose that we started with diameter 12. Then we redo the calculation. We find 4 diameters 12 or 450 square millimeters. And the maximum steel stress is then 260 megapascal. You see that 4 diameters 12 slightly better than 3 diameters 14. Just to demonstrate that when you don't know the diameter, you have to redo your calculation when you are not satisfied with your answer.